this question is a little different than some of the ones we've been doing. In this case, they tell us what the coefficient of static friction is, and it's pretty high. The mu s between the pavement and the rubber tires is 0.9. And what that means is the surfaces are pretty sticky. We know that. Imagine a car is parked on a steep slope, okay? They want to know what's the maximum angle you can actually park that car in order for it not to roll. Or not to roll, but not to slide down. So the wheels are locked. You maybe have your parking brake on. But if you imagine the theta getting bigger and bigger, there's going to reach a point where no matter how like locked your wheels are, this car is still going to slide down the slope. Imagine, I mean, maybe it's easier to imagine if it's like an ice storm or a rainstorm and the ground is slippery. But this is even true with concrete or cement, asphalt, and car tire. So we want to kind of know what theta are we dealing with in which the car is going to start sliding. So the best way to go about doing it is the same way we go about doing all of our problems. There's really no difference. What are the forces acting on the car? Let's take the middle one because it seems like a in-between example. The forces acting on the car are the same: gravity acting straight down, the normal force perpendicular, and we know there has to be friction because otherwise it would be accelerating for sure. We know it's at rest. So that's my force of friction, my force of gravity, my normal force. Interesting to note that they're the same three forces as in the previous problem with the kid on the toboggan. So the idea being is just the proportion. I mean, obviously this force is big enough to overcome the x component of gravity, which keeps the car in place. We know that mu s is 0. We also know that a equals 0. It's not moving, right? So let's start this problem in the usual way. And we're going to start it by F net equals sum of the forces. So let's go, okay, and you know, also you know that we're rotating our axes. If this car does slide, it's going to slide down the ramp. I don't think it's absolutely necessary in this case. You may want to consider not rotating your axis, but then that is another type of problem, and if you want to know about that, you can come and talk to me. I'm going to rotate the axis, so that's y, that's x. So let's look at this, because if it's going to slide, it's going to slide down that way. So let's look at it. Now, something that I think that maybe you might need a tip on this in terms of answering this question is, it says how steep, what maximum angle can you leave the car parked? What we're going to assume, we're making this assumption. What we're saying is, at this angle, the acceleration is going to be 0. It's not going to move. If I add 1 degree to this angle, suddenly I've overcome static friction and now it's going to be sliding down the ramp. So for this particular problem, I'm analyzing this problem at the limiting condition. I want to take this to be true. And this theta is at the limit. So what we're saying is at this theta, a is 0, but at this any theta greater than this one, it's going to start to move. So we can still analyze it as if it's using static friction here. So along the plane, or parallel to the plane, what we have is ma equals the sum of the forces. Now, taking the down to be positive, this along the plane down to be positive and friction to be negative, we have 0, right, because a is 0, equals fgx minus ff. So what we can see is that friction has to equal the x component of gravity. So let's expand these two expressions a little bit, because we know ff is mu fn, right? And we know that fgx is fg sine theta. We know those two things. So from this information, now we're at that point again where we need to go to the vertical to look at what the normal force is. So let's look at the perpendicular to the plane. And again, ma equals the sum of the forces. And in this example, a is again 0. It's not floating off the plane. It's not smashing into the plane or the slope. It's just at rest. And so the sum of the forces in this example is Fn minus Fgy. So we can see that Fn is equal to Fgy. Now we know that Fgy is equal to mg cosine of theta. And then we can plug that back in. We can plug this back into here. And I haven't put in any numbers, and it's a little disconcerting because the question doesn't tell us the mass, but when I get this, I get mu mg cosine theta equals, and then Fg is just mg sine theta. Well, look what I have. I have this really nice expression where I have an m on both sides, I have a g on both sides. So I end up with mu equals sine theta over cos theta. And I don't think it's a big stretch for you to know that this is tan theta. And so we get an expression mu equals tan theta. Hi, Harrison. So Harrison is here. I'm just going to finish this. Tan inverse. So that therefore we get expression mu is tan inverse of, sorry, theta is tan inverse of mu. And I think you figured out that I got the answers wrong in the first and second problem, but the angle works out to 42 degrees. Sound good?
Sounds good.